Today, we will talk about how choosing the right batch size can make our operations run smoother and more efficiently. We begin with a concept that is fundamental to our operations management: how capacity correlates with batch size. As we know, the principle is quite straightforward. As we increase the batch size, the setup time, which is a significant part of our operation, is distributed over more units. Essentially, this means we are able to accomplish more within the same time frame, thereby effectively increasing our process capacity. However, there's a limit to this increase. Even if we imagine a scenario with an infinite batch size, where setup time is completely eliminated, our process capacity can never surpass the inverse of the processing time. This represents the maximum capacity we could achieve with an infinite batch size. We are now examining a practical example of an assembly system that involves a mini machine and an assembly process. Our assembly system is comprised of two main stages. The first stage involves the use of a mini machine, which requires a 120 minutes setup time. The second stage is the assembly process, which has no setup time. Consider a scenario where we have a batch size of 12. In this case, the mini machine becomes the bottleneck in our process flow. Why is that? Well, due to the lack of setup time, the assembly process has a constant processing time of 1/3 unit per minute. When accounting for setup time, the throughput of the mini machine is calculated to be 0.0833 units per minute, making it the limiting factor. Now, let's scale up our operations. What happens when we increase our batch size to 300? Here, the table is 10. The assembly process becomes the bottleneck. So, we have a key question to ponder. What is the smallest batch size such that the mini machine does not constrain the process flow? Let's take a deep dive into the concepts of choosing the batch size to meet a specific target capacity. For our mini and assembly process, we have identified a target capacity of 1/3 unit per minute. This is derived from the constant capacity of the assembly process, which has no setup time. If the mini process has a lower capacity, it becomes the bottleneck, restricting the overall throughput of our assembly system. However, it is important to note that this presumption is based on the system being supplier constrained. If it wasn't, the demand rate would define our target capacity. So, a critical question emerges from this scenario. What is the minimum batch size that allows us to achieve our target capacity of 1/3 unit per minute? To answer the previous question, we will discuss the process of choosing the ideal batch size to meet a specific target capacity in our operations. To begin, let's consider the capacity equation. Capacity equals batch size divided by setup time plus batch size times processing time. By rearranging this equation, we can derive a formula that determines the batch size necessary to achieve our target capacity. Batch size equals capacity times setup time divided by 1 minus capacity times processing time. Now, let's apply this formula to our mini machine example. Batch size equals 1/3 times 120 divided by 1 minus 1/3 times 2 equals 120. With this calculation, we can conclude that a batch size of 120 units or more will ensure the mini machine's capacity is at least 1/3 unit per minute, equals to the assembly's capacity. In this segment of our discussion, we will delve into the relationship between batch size, idle time, and utilization. Idle time, which is the time spent not producing, consists of two parts, setup time and literal idle time, where the machine is neither producing nor setting up for production. Utilization, on the other hand, is defined as the time spent producing divided by the sum of the time spent producing and idle time. So, how does batch size play into this? As we increase the batch size, the utilization of the mini machine also increases, up until the point where it is no longer the bottleneck in our process. Beyond this point, the process may become demand constrained. We now examine a scenario involving small batch sizes and how it affects the utilization of our assembly process. Let's consider our mini machine example. Suppose we have a batch size of 80 component set. For both the rib and support components, the setup time equals 60 minutes each, and it takes 1 minute to produce 1 unit of either rib or support. In this scenario, the mini process becomes the bottleneck, requiring 280 minutes to produce a batch. Meanwhile, the assembly process only needs 80 times 3 or 240 minutes to produce the same batch. As a result, the assembly process must idle for 40 minutes with each batch to avoid overproduction. The situation affects the utilization rate of both processes. For assembly, the utilization rate is 240 over 280, or 85.7%. For mini, the utilization rate is lower at 160 divided by 280, or approximately 57%. Continuing from our previous example, let's now consider a scenario with a large batch size and observe its effect on the utilization of our assembly process. Suppose we have a batch size of 200 component set, again, operating under supplier constraint. In this situation, the assembly process becomes the bottleneck. It requires 3 times 200 or 600 minutes to produce 200 units. With this large batch size, the utilization rates for our processes change significantly. For example, the utilization rate is now 600 over 600, which equals 100%, a fully utilized assembly process. On the other hand, the milling process's utilization rate increases to 400 over 600, or approximately 67%. Understanding this shift in utilization with changes in batch size is critical to maximizing efficiency in our operations. As we proceed, we will discuss strategies to optimize these factors to achieve the best possible performance. Now, let's consider an additional factor related to large batch sizes. While larger batches can increase utilization rates and optimize capacity, they also have potential downsides. One significant drawback is that large batch sizes lead to more inventory within the process. This was evident in the utilization graphs we examined earlier. The increase in inventory can result in higher holding cost, more space requirement, and potential for waste due to obsolescence or damage. Therefore, as we optimize our operations, it is crucial to strike a balance. We need to manage batch sizes in a way that maximizes capacity and utilization, but without leading to excessive inventory. Moving forward, let's delve into a scenario that achieves a just right batch size. Consider a situation where our batch size is 120 component set, operating under supplier constraints. The assembly process in this case would require 3 times 120, or 360 minutes, to produce 120 units. This results in a utilization rate for assembly of 360 over 360, which equals 100%. Meanwhile, the milling process utilization rate will be 240 over 360, or approximately 67%. Notably, milling's utilization cannot be higher in this scenario. If it were, milling's actual production will exceed 67% times 1 second unit per minute, which equals 1/3 unit per minute. This would lead to a continuous, limitless growth in parts inventory, a situation we clearly want to avoid. So, choosing a batch size of 120 component set, we can achieve the lowest inventory level without decreasing the process capacity. It represents a balance that maximizes efficiency and minimizes inventory buildup, leading to a more effective and cost-efficient operation. Let's now consider the implications of our discussion so far, particularly with regards to inventory control through batching. From our exploration of different scenarios, we can derive an essential rule of thumb. If the setup occurs at a long bottleneck stage, we should decrease the batch size. This approach helps to avoid overproduction and unnecessary inventory buildup at these stages, which can lead to increased costs and efficiencies. On the other hand, if the setup occurs at the bottleneck stage, our strategy should be to increase the batch size. This helps to maximize the utilization of the bottleneck resource and maintain a steady flow of output, thereby increasing the overall efficiency of our operations. Now, we will be discussing a case study that illustrates the relationship between inventory and product variety, using the example of a soup production process. In this process, two kinds of soups are being made, chicken soup and tomato soup. The demand for chicken soup is 100 gallons per hour, while for tomato soup, it is 75 gallons per hour. The setup time for each soup is half an hour, and the production rate for each soup is 300 gallons per hour. For the purpose of our study, we will define our flow unit as 1 gallon of soup, which we will consider as a batch. We will also assume that we iterate between the production of chicken and tomato soups. We will be defining the batch size as the total quantity in gallons of both chicken and tomato soup. The question we aim to answer is, what batch size will minimize our inventory without affecting the demand for each soup? Let's delve into the analysis of our two soup case study. Firstly, we need to establish our target capacity, which is the sum of the demand for both types of soup, 100 gallons per hour for chicken soup and 75 gallons per hour for tomato soup. Therefore, our target capacity or flow rate is 100 plus 75, which equals 175 gallons per hour. We have to note that each batch involves producing both chicken and tomato soup, meaning the total setup time per batch, 1 gallon of either soup, is 2 times 0.5, equaling 1 hour. Also, the processing time is calculated as 1 over 300 hours per gallon. Using our capacity equation, which is batch size equals capacity times setup time divided by 1 minus capacity times processing time, we can calculate the recommended batch size. Plugging in our values, we get batch size of 175 times 2 times 0.5 divided by 1 minus 175 times 1 over 300, which equals approximately 220 gallons. For production proportional to demand, we will produce chicken soup equals 100 divided by 175 times 420, which is about 240 gallons. Tomato soup equals 75 divided by 175 times 420, which is about 180 gallons. This analysis allows us to maximize efficiency by minimizing inventory and still meeting demand for each type of soup.